All right, so this is our Unit 1 presentation. It's going to be based on the first few chapters on this book that's about probability and inductive logic. So the first chapter is about deductive logic. And with deductive logic, if your reasons or your premises are true, your conclusion is automatically going to follow, meaning that the conclusion is going to be true if your premises are true. And these are arguments that are based on essentially the definition of the words. So based on the definition of this word and based on the definition of some other words, you can make a conclusion that it has to be true. And simple arguments in math follow this type of pattern. So 2 plus 2 equals 4. So based on the definition of 2, based on the definition of addition, and based on the definition of 4, that has to be true, right? So if you change the definition of what 2 means or what plus means or what 4 means, you could change the argument around. But based on the definition of those words and based on the premises, like I have $2 and my friend Tim has $2 and we added them together, therefore we ended up with 4, there's really nothing else to be done there, right? You can't really disagree with that unless you're going to disagree about the definition of what numbers are, right? Now, if your argument is based on a fallacy or an error in reasoning, the argument is not going to be valid. But as long as you're not, as long as your reasoning is solid, it's going to be, deductive arguments are always going to be valid. That doesn't necessarily mean they're going to be sound, though. And the difference between a valid argument and a sound argument is kind of subtle. So I'd recommend taking a look at the difference between those two. Study that in the book a little bit, maybe do a little bit of online research and reflect on it. A lot of people mix those two things up. So a sound argument is one that is valid and when the premises are actually true. So an argument can be valid but not sound. And that happens when the structure of the argument is good and there's no fallacies involved, but one of the premises turns out to be false. And we'll look at an example of that here in a moment. Okay, there we go. So these are two structures that are pretty typical in deductive reasoning, and they're very similar to each other. Let's go ahead and look at the second one. For every f is g, b is f, therefore b is g. Let's fill in the blanks here. Let's say every dog is a mammal, and Tony is a dog, therefore Tony is a mammal. Now this argument is totally valid, but let's imagine a situation where one of the premises is false. Let's say Tony is not a dog, he's actually a tiger. And in that case, this argument is valid, but it's not sound because one of the premises is false. What makes it even more complicated is tigers happen to be mammals as well. So if we look at the conclusion, Tony is a mammal, the conclusion is actually true. So even though our argument is valid, it's unsound because one of the premises is false. But even though the argument is unsound, the conclusion still just happened to be true by coincidence, right? So untangling these types of arguments can be a little difficult. You have to think about whether the premises are true, whether the conclusion is true, and whether the conclusion follows from the premises, right? So there's a lot of options that can go down here. With inductive logic, the arguments are not necessarily going to produce a conclusion that's guaranteed. So what we do is we look at samples or populations to make some kind of conclusion. And there's some classic examples about ravens, right? So let's suppose we say all ravens are black because every raven we've ever seen was black. It might be extremely likely that all ravens are black, but what happens if you find a blue one? What happens if there's a such thing as an albino raven? There could be an exception to what you're looking at. So inductive arguments are based on essentially on data, and extrapolating from the information that you have to form some kind of conclusion. A lot of times they involve probability. And just because an argument involves probability, it doesn't mean that it's necessarily inductive. There are deductive types of reasoning that involve probability. And it is possible to make certain types of inductive arguments that are not based on probability. But it's the most common type, and it's the one that comes up in science quite often, right? So you can use inductive arguments to support a hypothesis, for example, or a plausible explanation. You can also base these on testimony. So suppose you're in a court, or really anywhere, but you have a reliable witness who's giving you a testimony about what happened. An inductive argument basically uses this information to come to some sort of conclusion. And if you have a very reliable witness who says they saw, Tony walk across the street at 2:00 p.m., you could perhaps build, an argument based on testimony like that, right? And so there's no deduction involved, but that doesn't mean you couldn't actually use that information in a reliable way, right? Okay. Let's also mention the gambler's fallacy a little bit. So what gamblers do is they assume they can predict the future results based on the past results, right? So they look at a pattern on the roulette wheel, or they look at a pattern in dice throws, and they know that certain patterns are unlikely to occur. And so based on past observations, they imagine that they can predict the future, right? And there's some issues with that. So there's two main factors in looking at scenarios of probability like this. You want to be looking at a game that involves being unbiased. So if you have some dice that each side is geometrically identical, so that when you roll the dice, it's equally likely that you'll land a 1, 2, 3, 4, 5, or 6. That's an unbiased scenario. And when gamblers go to a casino, for example, and they trust that the decks of cards are the way that they're supposed to be, and you're not more likely to pull a 2 out than a 3, and they look at the dice and they assume that they're geometrically formed correctly into the right shape of cube. And so they know that these are unbiased results. They don't, assuming that there's not 5 3s in the deck and only, 3 2s. And so there's unbalance there. It's biased in favor of 3s. And assuming that the one side of the dice, isn't bigger than the other, so it's more likely to happen, the gambler is comfortable going in there and, making decisions. The other issue is independence. So in a fair game of chance, you want each trial to be independent of the others. So if I take my dice and I roll them once, and then I pick the dice up and roll them again, the second result should be completely independent of the first. They should have nothing to do with each other, right? So when you're a gambler and you think you can predict the future based on the past, you're correctly applying the idea that these are unbiased, so the game is fair in that sense. But you're forgetting that the trials are independent from each other. So when you roll a pair of dice the second time, the dice don't know that you already rolled them before. There's nothing in nature that records how you rolled the dice in previous rolls that can influence future dice rolls. So each one is completely independent, and you can't really judge what's going to happen based on previous dice rolls, right? So thinking about these two, we can imagine another game where, let me see if I have this one described. Yeah, so suppose we have an urn, right? And we put 50 green balls in there and 50 red balls, and we're going to draw one out, right? Sort of like similar to kind of a lotto scenario where they draw numbers out, something like that. If there's an equal number and I pull one out, it's unbiased in the sense that there's a 50-50 chance that I'm going to get a red or 50-50 chance I'm going to get a green. Now suppose that suppose I draw a green and then I put it back in and then I draw again. Those two, the second draw is still going to be unbiased because I didn't replace it. But let's suppose I pull a green out and then set it aside and then draw again. On the second draw, I'm more likely to pick out a red because now there are more red inside the urn than green, right? So those two, in the second case that I described, those are not independent draws, right? What happens next depends on the previous sample. Okay? So you can have scenarios where the game of chance is biased or unbiased. You can have games of chance where the trials are independent or dependent on previous examples. And for a game to be fair, you want it to be independent and unbiased.